All right, lesson 4, many body problems. Problems, Sydney, with more than one mass. We're going to cheat. If there's more than one mass, we're going to pretend it's all one mass if they're attached by a rope. That's the short answer. I could almost jump to your homework right now, except I want to work through a few examples. It says this. In these problems, we have several objects connected together by strings, by a rope. The easy approach is to realize that we can treat the system as a single object because all parts are traveling at the same rate. Example 1. So I have a 3 kilogram mass, I have a 2 kilogram mass, they're attached by a rope, and then I have a 20 Newton applied force tugging it. Oh, and it says find the acceleration and find the string tensions. So here is the system approach. We're going to treat this as a single object for our equation. We're going to write an equation that has both masses in it. It's going to look like this. The first thing we're going to do is we're going to do a free body diagram. Although instead of doing a complete free body diagram where I redraw each mass, Terry, as a dot, I'm just going to label the forces on the diagram that they gave me. Since they didn't specifically say, draw a free body diagram for Marx, I'll skip that. So I'm going to say, Terry, my friend, what are the forces acting on this 3 kilogram mass? Get the obvious one. And since there's two masses, I'm going to call this M1G. So all of our numbering looks the same, Jake. Let's decide we're going to go from left to right, and the first mass we're going to call M1. Jake, what would we call the second mass? M3? No, M2. Yeah, right? Okay. Terry, is this sinking into the ground? No. Is it lifting into the air? Then I think there's a balancing equally sized force in the opposite direction. What is that force, Terry? And I'm going to call it Fn number 1 because I notice there's another mass also touching a surface. I think there's more than one normal force. What else? There is one more. Is there friction, by the way? And how can you tell? Look closely at the picture. Zero friction this time. We'll add friction. There is one more force. Just tension, not the 20. Tension. The rope is what's pulling that guy forward. Let's go over to this 2 kilogram mass. What are the forces acting on it, Sebastian? Get the obvious one. And I'll call that M2G. Is that okay? Do you mind? Is it sinking into the ground? No. Is it lifting into the air? No. There must be a force in the opposite direction. Which one? And can I call that normal force number 2? What else? Well, obviously there's the applied force in this direction, 20. What else? There is one more. Tension going backwards. Tension going back, because it's also got a rope. What really is happening, Sydney, is that 2 kilogram is tugging on the 3 kilogram, which is slowing it down. There's our free body diagram. Vertically, Chelsea, can you see that my forces are all in balance, that the normal equals mg1 and normal 2 equals m2g? Okay. Horizontally, who's winning? I think the applied force. I think my equation's going to look like this. So now that I've decided that my applied force is winning, anything to the right is going to be winner, positive. Anything pointing to the left, Jake, is going to be loser, negative. So let's walk down this rope here, and I see 20. Let's keep walking, let's keep walking. I run into tension. Which way is tension pointing, left or right? Loser! I mean, the force, not you. Okay. Although you were late, maybe I should. Okay. But Jaron, then I run into a second tension pointing which way? Winner! Have I walked through all of the horizontal forces? Yep. Now, by the way, if there was friction, can you see where they would fit in? I'd have a couple of friction forces kicking around as well. It's not that much tougher to add friction to this if we use this approach. But there are none. And this is going to be, did I look at forces from more than one object, Josh? Yeah. Then it's going to be the mass of object 1 plus the mass of object 2 times A. My argument here, Taylor, is, look, since they're attached by a rope, they must be accelerating at the same rate because they're attached by a rope. I defy you to tug on something with the rope and have the second object accelerate differently from the first object unless you give a big jerk or a yank, and we're not doing that. Smooth pulls. Oh, Mr. Dewick is relaxed. Why is Mr. Dewick relaxed? What happens to the tension? And anytime he loses tension, he's more relaxed. Okay, lame joke. Tensions cancel. Oh! How would I get the acceleration by itself? Really? Huh? Divide by both masses. I think my final equation is going to look like this. The acceleration is going to be 20 divided by mass 1 plus mass 2. Don't get out your calculators. We can do this in our heads because it's going to be 3 plus 2. What is 3 plus 2 in your head? 5. What's 20 divided by 5 in your head? So we've cooked the numbers for some nice ones here. 4. Why is that wrong? Because it is. Yeah, sig figs, Megan, 2 or 3. Yeah, 2 or 3. 4.0. Okay. So if they give me more than one mass and they want me to find the overall acceleration, can you hear, Alicia, in the word overall? I'm suggesting use all of the mass. It contains the word all. You go, draw your forces on everything, walk down the line. Everything to the winner is positive, everything to the loser is negative. And if you do it right, your tensions would cancel. Your tensions will what? They'll cancel. But part B, or the second part, says find the tension. Okay. To find the tension, Tyler, look at a single solitary mass. We're going to isolate a mass. Let's look at the 3 kilogram one. Tyler, do you remember what were the forces acting on this 3 kilogram mass? Get the obvious ones? Gravity down. Those are the only 3 forces. Okay. Vertically, is anything special going on? I think we're in balance vertically, Jake, so kind of, boring. Horizontally. Tyler, who's winning? There's only one horizontal force, so who's winning? Now my equation is going to be winner. Any losers? Nope. And that's going to be, now careful, am I looking at both masses right now or just a single solitary mass? M1A. Do I know M1? Yeah. Do I know A? Oh, I just figured it out by looking at all of the masses, which is why, Terry, I had to do that first. In fact, I don't need a calculator for this either. I think it's going to be 3 times 4 in your head, Tyler. What is 3 times 4? Woohoo! 12 what? With authority, like you know what you're talking about. 12 what? 12 newtons. The nice thing about this system, Jason, is supposing instead of looking at the first mass, you had decided to look at the second mass and use that to find tension. It works as well. If I drew the free body diagram on the second mass, you may recall, Jason, I had M2G, normal force 2. I had the applied, and I had tension. Jason, in mass 2, who's winning? Which is how big? So you would go like this. 20, you would say minus tension, because tension is now a loser, and that equals, since we're only looking at one mass, M2G. Can you see to get the I think to get the tension by itself, the easiest way, Jason, would be plus that to this side, minus that to this side. Can we do that one step? I hope. Tension is going to be 20 minus M2G. It's going to be 20 minus, Jason, what was mass 2? How big? 2. What was the acceleration? Sorry, I wrote G, Mr. Dewick. That's silly. It's not G. It's A, Mr. Dewick, because it equals MA, Mr. Dewick. It equals MA, Mr. Did it again. Good gosh. Equals MA, Mr. Dewick. Sorry, guys. What's A, which we figured out? Oh, it's 20 minus 8. Do you get the same answer as we got with the other mass? Cool. Also 12 newtons. That's going to be our approach. You give me more than one mass, I'm going to look at the overall mass to find the overall acceleration, and then look at one mass to find tension. Or this year, because we did this a little bit last year, I would have no problem giving you the tension. If they give you the tension, look at one mass to find the acceleration, and then you can use the overall acceleration to find any mystery masses or anything else that you're missing. So this works both forwards and backwards. If they want acceleration, you know both masses, look at all the masses, find acceleration, then find t. If you don't know all of the masses, I guarantee they'll tell you tension. Or they'll tell you the acceleration, but you can use this to hopscotch your way around. When we have several masses connected by strings, we need to realize that the first string accelerates the first mass, but the second string accelerates both of the first two masses. Example 2, find the acceleration and the chord tensions. Okay. I guess we'll go M1, M2, and M3. Let's start out with M1. What are the forces acting on M1? Get the obvious one. M1G. Normal force 1. What's pulling it forwards? And is there more than one rope in this question, Mabad? Say yes. Right here and right here. Yes? Is there more than one rope in this question? Say yes. So I'm going to call this, how about tension 1? Let's go to this 2 kilogram mass. What are the forces acting on it, Mabad? Get the obvious one. I totally agree. And normal force number 2. What's pulling it forwards? Ah, he can be taught. Tension 2. What's slowing it down? Tension 1. Let's look at the third mass. M3G. Normal force number 3. The applied force, and what's slowing it down? Tension 2. Gabby, who's winning? How big? So here's my equation. Winner. And now I'm going to walk, by the way, vertically, Gabby, you'll notice everything is in balance. Is he okay? You sure? Because he's here now. Thank you. You are so good to be his friend, by the way. It's very nice of you. You're good, Jaron? Yeah? Okay. Let's walk down. Vertically, all my forces are in balance, which is why I jumped straight to horizontal. Let's walk down this. So here I run into tension 2. That's a loser. Oh, but I also run into a winner, tension 2. And I run into a loser, tension 1. Ooh, but I run into a winner, tension 1. I've walked down the whole length of rope. Dorothy, this time I've looked at 3 masses. So over on the right-hand side, instead of saying MA, it's really going to be M all A, or M1 plus M2 plus M3, whichever one you want to write. For me, writing M, all of them together, is shorter. All of the masses times A. Why is Mr. Duick relaxed? Oh, I'm losing tension all over the place. Jaron came, so I'm not mad anymore. I thought I was going to have to get mad at him for missing a test, but no, he's here. And when you do that, this equation simplifies tremendously, because how would I get the A by itself? Divide. Yeah, in fact, I get this. Hey, dudes, the acceleration is 20 divided by M1 plus M2 plus M3. It's 20 divided by... I don't need a calculator for this either. Is it 20 divided by 10? Yes? Which, in your head, Ben, is what? And why is 2 wrong? Okay, so 2.0. Nice. Now, let's find the tensions. To find tension 1, Sydney, the easiest mass to use is going to be mass 1, because you notice the only horizontal force on it is tension. I would use that to find tension 1. To find tension 2, I probably wouldn't use the middle mass, because to find tension 2, I would have to use tension 1, which would guarantee if I got tension 1 wrong, that would guarantee that I got tension 2 wrong. To find tension 2, I would use this one, 20 minus T2, because I know the 20 is right because the diagram gave it to me. It's not wrong to do it other ways, but Alicia, I'm trying to be a good test writer as well and hedge my bets whenever possible. So let's find tension 1. That's going to be M1G, normal force 1, tension 1, winner, equals, and now I'm just looking at a single solitary mass, it's going to be M1A. Tension 1 is going to be 2. Sorry, not 2, Mr. Dewick. The mass is 3. The acceleration is 2. 3 times 2. I can do this in my head, too. Oh, look at that. 6.0. Tyler, 6.0 what? Newtons with authority, like you know what you're talking about. I'm going to get it from you yet. Newtons? Newtons. Is that okay? Next page. Chord 2. Now, I noticed when we set this up, they have me using mass 2 to find chord 2, because I noticed they left mass 3 blank. I'm going to use mass 3 because I think that's a smarter way to do it. So I'm going to quickly over here write in the 5, and I'm going to say over here I have M3G, normal force 3, 20, tension 2, and I'm going to say 20 is winning minus tension 2 equals M3A. I'm going to say tension equals 20 minus M3A, and that's tension 2, Mr. Dewick. It's going to be 20 minus 5 times, what was A, 2? Newtons. It is 10, yes? Consistency check. So if I finished this test early, now I would go back, Chelsea, and I would check on the middle one. And if I get the same answer there, yay, I probably got all of them right. So I would say, okay, over here I have tension 2, tension 1, normal force 2, M2G. I would say tension 2 minus tension 1 equals M2A. I would say, well, tension 2 equals M2A plus tension 1. M2 is 2, A is 2. What was tension 1 from the previous page? I've forgotten. Was it 6? Do I get the same answer as we got previously? I do. Yay, we're right. Okay. Now here's the nice thing. This approach even works if you have a hanging mass. Because I'm going to argue with you that if I have one mass on a surface like this and one mass hanging down on a pulley like that, they're still going to accelerate at the same rate. One's going to be down and one's going to be to the right, but the rate is still going to be the same. Or if I have somebody pulling, they're still going to be accelerating to the left and up at the same rate. All that's going to change is my free body diagrams. Specifically, Megan, if I have a mass hanging in midair over a cliff like this, is it touching a surface? So is there a normal force? Oh, it makes it easier. So if we have a hanging mass and no external force, we need to understand it's the weight, the mg of the hanging mass that accelerates the entire system. So it says identify the net force and then find the accelerations and the chord tensions. I like this question. I like this. Oh, you know what, though? There's no friction. I like this question if there was friction. I like this question if there was friction. If there was friction, this would be a nice question. You ready? Let's find out. What are the forces acting on this 2 kilogram mass? Get the obvious one, Chelsea. I'll call it M1G because there's 2 masses. What else? Normal force, absolutely. What else? There's a rope. What else? Nothing. If I had friction, I would point friction to the left. And be an easy thing to add into my equation. Let's go look at this hanging mass. Charles, what are the forces on the 4 kilogram mass? Get the obvious one. Darn right. What else? Is it in free fall? Is it free falling at 9.8 meters per second? No, so there has to be a force up. What? Give you a hint. There's a rope. There's a rope. There's a... See it? Oh, and is it the same piece of rope that's connecting the 2 kilogram? Then those two tensions are the same. Who's winning? Well, I'm pretty sure this thing is not moving to the left because there's nothing pulling it to the left. It's accelerating to the right. This is accelerating down. What is the force that's getting this whole thing to move? There's the winner. Who's winning? M2G. So now I'm going to walk along this rope, and any forces that when I follow them through the rope, Jason, end up pointing down will be winner. Any forces that when I follow them through the rope end up pointing up will be loser. Winner. Walk along the rope. I run into this first tension here. Winner or loser? Pointing upwards in the opposite of gravity. Loser. But look at this second tension here that I run into when I continue along the rope. If I follow this second tension down, I think it ends up pointing downwards. Yes? In the winner direction? And that equals, did I look at forces from both masses in this equation? I did. It's going to be M1 plus M2 times A. Ben, you're looking relaxed. Why are you looking relaxed? Oh, you're losing tension? Oh, it's always good. Ben, how would you get the A by itself? Oh, by the way, before I go further, can you see if I did have friction here, I would just have one more loser over here, and then I would say friction is what times what? Mu times the normal force. I don't know the normal force. Look, 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 look. I don't know the force same size as the normal force, mg. It'd be easy enough to add in there. It would just give me a bit more calculator work to do. Sorry, Ben, what'd you say? So you're telling me that A equals M2G all divided by M1 plus M2? By the way, let's look at this. What would happen if this mass got bigger, if this was heavier? What would happen to this number right here? It's meant to be really obvious. Get bigger. What would happen to the denominator? Gets bigger. So what happens to your overall acceleration? If you divide by a bigger number, what happens to your answer? It doesn't accelerate. What we're really saying is, hey, this gets bigger and bigger and bigger. This doesn't move as fast because gravity can only tug so hard. And gravity's only tugging on this guy through the rope. Okay. What do you get? Let's put in the numbers, I guess we should. 4 times 9.8 divided by 6. 4 times 9.8 divided by 6. 6.533333. A equals 6.53. Tyler, units. Meters per second squared. Yes. Okay. By the way, it says the net force accelerating the system is, I wrote the acceleration there because we did the whole thing in one fell swoop. I actually didn't even bother finding the net force. I just said we can solve this. Oh, let's find tension. Which is going to be an easier mass to find tension in? Mass 1 or mass 2? Now, in this case, it doesn't matter, but mass 1, the first mass, is going to be easier to find tension in because it's only got one horizontal force acting on it. It's only got that guy right there. So I could go like this. Looking at mass 1, who's winning? Tension. Who's losing? No one. Equals mass 1A. 2 times 6.53333, 13.1 newtons. Alicia, we could also have looked at this mass. Who's winning? M2G. Who's losing? Tension. And you would have M2G minus tension equals M2A, because you're looking at one mass. And you get the same answer. Says, for problems that involve friction, on the next page, we can still use the system approach to find the acceleration, but tension calculations are a little bit trickier because you may guess wrong. Example 4 says, explain how you would find the acceleration of each system. Well, what are the forces acting on M1? Get the obvious ones. What else? Normal force 1. Tension. Now there is friction because there is a mu down here. I would call that friction force number 1. What are the forces acting on mass 2? Get the obvious ones. I would say, okay, M2G, normal force 2. I got the applied force over here. I have tension. Oh, and I also have a second friction force slowing it down. The only way this thing is going to move is, can anybody see? If what? For this to move, what needs to be true? F applied has to be bigger than if it's not, you know what your acceleration is? 0. Because it's not moving to the left. You may calculate the forces of friction. That's bigger than F applied. It's going to move to the left. No, remember we said friction is only as big as it needs to be. Here, kind of the same idea. Here we would have our usual bag of tricks. M1G, normal force number 1, tension, friction. Here we would have M2G and tension. Why no normal force? It's hanging in midair. What's the only way this can accelerate? The only way this can accelerate gravity pulling the second mass down has to be bigger than friction force number 1. So it would be possible, Josh, for me to say, hey, let's put a 5 kilogram mass there and a 2,000 kilogram mass in mass 1. You know what? That 2,000 kilogram mass will allow this to hang over the cliff quite nicely. It's what rock climbers do all the time when they're holding a partner, when they're rappelling down. They dig in their spikes, or they press against a rock, or they'll lash it to a rope. They're doing anything they can. They want to have a bigger force up here so that gravity doesn't win. Okay. Mr. Duick, what if you're not sure? If you're not sure, guess. What if you guess wrong? How can you tell you guess wrong? What will you notice with your acceleration? It's going to be negative. Oh, and did I show you earlier? It's fairly easy to fix that. The only thing is, if you guessed wrong, if you had it accelerating to the right and it's actually accelerating to the left, your frictions are all pointing in the wrong direction. You will have to fix your free body diagram a bit more than in the example that I did earlier today, where we just changed every plus to a minus and every minus to a plus. You have to change it a bit more. So I look at this one and I say, it says find the overall acceleration and then find the tension. I think that 20 is winning. Let's see. I think I would go yoink, M1G, normal force 1. There is friction. there is tension. M2G, normal force 2, the applied force of 20, tension, and there's going to be some friction as well. I'll call that friction force number 2. Who's winning? I don't know. Who am I going to guess is winning? 20. So now I'm committed. 20 minus, that's walk down the rope. I run into friction 2, which is pointing to the left, and so therefore, Megan, it's a loser. I run into tension, which is pointing to the left, and so therefore, it's a loser. Oh, I also run into tension again. Yay! Oh, and I run into friction force number 1, which Tyler is going to be a loser. Did I look at more than one mass? Then you know what my equation on the right is going to be? Not MA, but what?
M1 plus M2.
Yes. Okay. Brian, why am I relaxed? Ah, nice. Okay, let's fill in what we can here. So it's going to be 20 minus, friction is what times what? Mu times the normal force. Oh, crap, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? So this time it's going to be mu m1g minus mu m2g equals, and how would I get the A by itself? Yoink. Divide by mass 1 and mass 2. And I hope what you're seeing here with this approach, Jake, is the questions don't get, like I'm not doing anything new, the questions get longer, but not much tougher. I just got more expressions. Okay, now we were doing some in our head. We're not doing these in our head anymore. The acceleration is going to be 20 minus 0.15 times 5 times 9.8 minus 0.15 times 3 times 9.8, all divided by 8, 5 plus 3. What do we get? Bracket 20 minus 0.15 times 5 times 9.8 minus 0.15 times 3 times 9.8, close bracket, divided by 8. Do you get 1.03? Megan, what are my units? What did we just... Yes. Did your physics teacher last year tell you it was worth memorizing it? Yeah. Okay. Let's see, how many more am I doing? Oh, one more and I'm done. Okay, that works. I was going, holy smokes, I'm only halfway down the lesson. But then I went, oh yeah, each question is a picture and takes like half a page. So the homework is like 5 pages long, but it's only 6 questions or something like that. Find the acceleration of the system, find the tension on each chord. Okay. Let's try this. 3 masses. Is 3 masses going to be tougher? Ben, I'm going to argue it's going to be longer. I'll be more careful. Oh, and it's not going to be equals m1 plus m2 times A. It's going to be equals m1 plus m2 plus m3 times A. Okay. Here we go. How am I going to start? Yeah, free body diagram. Although I'm not going to redraw everything. I'll label the forces on my original diagrams. Okay. Let's see. We got M1G. Normal force 1. Tension 1. Why did I put tension 1? How many ropes are there in this picture? 2? 2, right? 1, 2. Friction force 1. M2G. Normal force 2. Tension 2. Tension 1. Yoink. Friction force 2. I usually drop my friction force down just so it stands out a little bit. That's why this is also isn't technically a free body diagram, because the force should be on it. Anyways. M3G. Tension 2. Is there a normal force on the third mass? Nope. And if there's a normal force, can there be a force of friction? No, because friction is mu times the normal force. And if normal force is 0, so is friction. Okay. Who's winning? M3G. So anything that ends up pointing down is going to be a winner. Let's walk along the rope. I run into a negative tension 2. Oh, I run into a positive tension 2. I run into a negative force of friction 2. I run into a negative tension 1. I run into a positive tension 1. I run into a negative force of friction 1. And I could have written mass of all, or M1 plus M2 plus M3. I'm doing both to show you, pick whichever one you like better. Question over there, or we're good? Good?
Isn't the weight up top more though?
Let's find, but the weight isn't what's, mg isn't what's slowing that mass down, it's friction. What you really want to be asking is the friction up top more than that force there? If the friction is more, then it ain't going anywhere. But if this is on ice, I'm telling you, even if this is 10 kilograms and 10 kilograms, a 5 kilogram is going to pull it off the cliff if it's on ice. It's going to slip. Right? That's what we're getting at. Good question. Glad you asked. Oh, Jake, you're looking less stressful. How come? Oh, gone. I didn't want to quite do that, Mr. Duke. Let's bring it back. Oh. Come back. Okay, let's try that again without hitting the erase button. Gone, 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 gone. Mr. Duke, could we just skip writing the tensions? I encourage you to write them in, first of all, because mathematically it's correct. The nerd within me does enjoy canceling things, but I think it's a good systematic approach. I think my final equation then is going to be this. Jake, how would I get the A by itself? So let's see if we can do that. We're going to go A equals, I'm going to have M3G. Yes? Minus friction 2. Friction force 2. Friction is what times what? It would be mu normal force 2. Stop, don't write that down. I don't know the normal force 2. Oh, but look at my free body diagram. I know another force the same size as normal force number 2. What? M2G. Now, again, have you ever heard me say friction is mu mg? No, I'm always saying friction is mu times the normal force. And until today, that will almost always be mg. It won't be after today. So, you're saying that this was, Tyler, my friend, M2G minus, and then I run into friction 1. Friction 1 is mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? M1G. And then, Jake, you told us divide everything by... And this also, Jaron and Jake, answers your question, because can you see, I hope you can see, if these two masses get bigger, the acceleration is going to get smaller, but it's not going to hit 0. The only way it's going to hit 0 is if this and this are bigger than that. But the denominator can't make an answer of 0. You can just make it smaller and smaller and smaller. Is that all right? Let's crunch the numbers. See what we get. 5 times 9.8 minus 0.2 times 3 times 9.8 minus 0.2 times 4 times 9.8 all over 4 plus 3 plus 5. 4 plus 3 is 12. 4 plus 3 is 7 plus 5 is 12. Have I got lots of room? Good. What's my acceleration? 2.94. Anybody else? Yeah? Even or? That's one of the things they wanted me to find, so I'll put a lovely box around it. What else did they want me to find? Oh, tensions. Okay, let's go looking at one mass. Let's find tension 1 first. Tension 1 appears in mass 1 and mass 2. I think it's going to be easier to find tension 1 from mass 1. Yes? So here's mass 1. What are the forces acting on it? Well, I got my picture here. Who's winning? What's pulling mass 1 to the right? Tension 1. What's slowing it down? Friction 1. So my equation is going to be tension 1 minus friction 1 equals mass 1A. My equation is going to be tension 1 equals M1A plus friction 1. Oh, friction is what times what? Mu times the normal force. I don't know the normal force. Look, 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 look. I know the force is the same size as the normal force. I think I can say plus mu M1G. Yeah? I think I can say tension 1 is going to be, what was mass 1? 4 times 2.94 plus 0.2 times 4 times 9.8. What's the tension in the rope number 1? $19.6. Let's go find tension 2. I could use the middle mass. I'm telling you, the right-hand mass, the hanging mass, is going to be way easier to find tension 2. You know what? It's got less forces on it. Less work. Who's winning in the third mass, in the hanging mass? M3G, right? Gravity. Who's losing? Tension 2. So here, my equation is going to look like this. M3G minus tension 2 equals M3A. Now I'm looking at just at one mass. I think we're going to get tension 2 equals M3G minus M3A. Tension 2 is going to be, what was mass 3? 5 times 9.8 minus 5 times 2.94. And I get 34.3 newtons. Okay. Friction, no friction. They're about the same. Sydney, a little more work with friction. Be carefuler. One mass, two mass, three mass, they're attached by a rope. They're all going at the same acceleration anyhow. What's your homework? Let's say number 2. Four. 5. Let's get something with some friction in here. Here we go. 7, 8, 9. Um, let's go 12B. You have different coefficients of friction because they're made of different materials. And 13 is tough. Well, finding the acceleration is pretty easy. For 13, how much is this little tiny mass on the top? 2. How much is the big mass on the bottom? I would treat it like one 14-kilogram mass. Find the acceleration. But the second part says find the coefficient of friction at the top. I'll let you think about that. Otherwise, I'll be talking about that one next class. But I'm curious to see who can figure it out. Maybe. Sure, let's do 14. Okay.